Okay, so at this point, we're going to do a Rockwell hardness test on this. The blades are still soft; they're in an annealed state, but they've been rough ground. So all the rough marks, all the forging, hammer marks, all that stuff, they're all gone. And so since it's been surface ground, we have nice parallel surfaces to use on this. This is a Rockwell hardness tester. It's a non-destructive form of testing, and to explain the gist of this thing, right in here is a diamond penetrator. It's a little diamond point, and that is pushed down into the steel, and this machine reads how far it's able to push that penetrator down into the steel, and the further it can push it in, obviously the softer the material. The softer the material, the lower the number on the Rockwell scale. The harder it is, the higher the number. So normally there would be no point in testing one at this stage. It's more important to know what it is once it's been hardened, but I wanted to do sort of a before and after so you guys could see the changes that will happen in the steel when we go into the last phase of the heat treating, which is the hardening and tempering. So the steel is put up here on this is called the anvil. It's raised up against the point and ran around 3 times on this main needle up to 12 o'clock, and then you pull a loading lever, and that's pushing that diamond penetrator down into the material now. But when this comes to rest, that won't be our final reading. There's a secondary lever over here that you have to release, and that'll allow the needle to swing around to what our actual final Rockwell reading will be. They say just to wait till the needle stops, but I like to wait until the handle is come to rest before I flip it. Okay, it stopped. I push this back around, and it's right around 19 Rockwell right now, which is very, very soft. Once we harden it, when we heat it up and quench it, it's going to be really hard, like 66, 67, and then we're going to temper these back to about 59 Rockwell. Okay, so I talked about the salt bath in the first part. We've got it running now at the target temperature, 1475 Fahrenheit, and the blades are all rough ground and ready to go into the last high heat phase of hardening. And so they're clean, they're dry, they're ready to go in. I wanted to mention that somehow it got edited out of the first part. It is absolutely critical that you do not introduce any moisture into the molten salt. Anybody who's ever worked around molten lead, pouring sinkers, jigs, bullets, can tell you, with lead you're working around about a 400-degree range when it's in its molten state. And that's still plenty high enough above the evaporation point of water that if you introduce any kind of moisture into molten lead, that moisture, it will immediately evaporate, and what that means in application is it's going to spit out and land on whatever is nearby. And so you can imagine we have that exact same concern with the salt, except for we're dealing with nearly 1500 degree temperature here, and also the salt has about the same viscosity of water. It's very fluid, so you absolutely don't want to be messing around with this. You want to make sure that the blades are definitely dry, because it doesn't even have to be a drop of water, just any moisture on the blade. When you have two dogs that can stick their nose on a kitchen counter without getting up off of their flat feet, and they really like to drink a lot of water, I got to be extra careful with them around this, because that could cause some major problems. But blade's dry, it's clean, it's rough ground. I tacked the washers back onto the tank, and we're going to lower it down here nice and slow. Let that come back up to the target temperature, and that'll be an austenizing heat. We're going to soak at that temperature for about 10 minutes. A tall vertical tank like this, especially having the blades hanging on a wire, because you can move the blade up and down to agitate it in the oil. Right now, as this blade is cooling down from what was the austenizing heat at 1475 and cooling down towards room temperature, the steel is transforming into martensite, which is a very hard structure, and it's also very brittle. And so right now, this blade, as it's cooling down, it should be reaching about 66 to 67 on that Rockwell tester. Now I'm not going to go test it, because the steel is like us knife makers like to say, it's screaming hard right now. You cannot get this steel any harder than it is right now at this point, as long as the transformation is complete. And so if you were to take this and huck it across the parking lot, when it hit the ground on the other side, it would most likely break into several pieces. It probably wouldn't shatter like glass, but it would definitely break in at least a few spots. And so with that kind of brittleness, with that high hardness, if we take it in there and set it on that machine and let that diamond penetrator push down into the steel, we put it at a very high risk of fracturing it, of causing cracking around that diamond point, which obviously we don't want to do. And so the very next step is going to be to get the oil cleaned off of this and then get it in a tempering oven. And then I go right into a detergent bucket. Get some of this oil off here before it goes into the tempering phase. Alright, we're on the other side of the shop, and the blade was taken from the salt, put into the oil, so it's hard, it's very brittle, it's fragile, and needs to be tempered back at a low temperature, which for me, the first cycle is going to be at 385 degrees Fahrenheit. I have had a lot of people ask me, well, why don't you use that fancy knife maker's kiln that you have for the tempering? And it has a pretty broad swing in temperature control on the low end. If we're up in the higher end, up above 1,000 degrees, it has a pretty accurate ability to hold temp. But when you get down to what we're doing here, around 400 degrees, it tends to swing up above and below that temperature, which we definitely don't want that. And I sort of inherited this with the shop, and just a regular household kitchen oven, but I've checked it with 3 different thermocouples, temperature probes, and it holds temperature really accurately in this range, and so in that temperature range. And so this is what I use for all the tempering on simple steels like these. And so the blade is scrubbed clean, got the oil off of it, and there's a piece of aluminum tubing in here, square tubing with some channels cut into it to slide the blade into, and we're gonna cook it for about an hour at 385, and that will draw out that hardness. It'll soften the steel just enough that we can check it for things like warpage, make sure we don't have any cracks in it. We can actually do a Rockwell hardness test on it again. And this is a lower temperature range. We're probably gonna have to go up above this in subsequent tempering cycles, but this is a good place to start for this steel. So let's go ahead and throw it in there. Okay, the blades have all been through 3 tempering cycles, and so in this last heat we take the sesame, ginger, and Greek yogurt marinated chicken breasts that have been in the refrigerator for 24 hours, and we cook those in the oven while it's still hot.